Good evening and welcome. My name is Ben Tudelo, and I'm an assistant professor in the Department of Geoscience in the Faculty of Science and the Gallagher Colloquium Series lead. Thank you for joining us online for this evening's Gallagher Colloquium lecture. We are recording today's session, and we will be posting this video on the Faculty of Science website. I encourage you to check out our website, science.ucalgary.ca, for event listings and video updates. One quick housekeeping detail unique to tonight's lecture format. If our webinar becomes disconnected before the event ends, allow us a minute to reconnect and start the webinar up again. You will be able to rejoin the webinar by using the same login link. Hosting this year's series online provides us with a greater opportunity to engage with attendees from around the globe. As we gather this evening, I like to think about who I'm sharing this virtual space with right now, both near and far. We are broadcasting from Calgary, which is located on the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, the Piikani, the Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, including the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to Métis Nation of Alberta, Region 3. University of Calgary is situated on land adjacent to where the Bow River meets the Elbow River, and that the traditional Blackfoot name of this place is Mohkinstsis, which we now call the city of Calgary. Before we begin tonight's presentation, I'd like to take a moment to recognize the Gallagher family for making this series possible. Through their generous philanthropy and vision for deep connection between the university and the community, the Gallagher family has provided the Department of Geoscience and the Faculty of Science with the opportunity to develop and grow the Gallagher Colloquium series, to strengthen our scientific community by increasing scientific knowledge, creating public awareness, and establishing connections with our alumni, community, students, faculty, and staff. Thank you, Tom and Fred Gallagher, for your continued support of this public lecture series and for being champions of science. The Gallagher Colloquium series continues to be an invaluable way to connect science with our community and our community with science. Now it is my distinct pleasure to introduce tonight's speaker, Dr. Susan L. Brantley. Dr. Brantley is a distinguished professor of geosciences in the College of Earth and Mineral Sciences and director of Earth and Environmental Systems Institute at the Pennsylvania State University. Dr. Brantley's career as a geochemist focuses on the chemistry of natural waters, both at the surface of the Earth and deeper in the crust. Much of her research is an attempt to understand what controls the chemistry of natural water and how water interacts with the rocks through which it flows. Dr. Brantley is a member of the National Academy of Sciences and fellow of the American Geophysical Union, the Geological Society of America, the Geochemical Society, the European Association for Geochemistry, the International Association of Geochemistry. She is a recipient of the Robert Gerolds Award from the Geobiology Society, the Urey Award from the European Association of Geochemistry, the Geochemistry Division Medal from the American Chemical Society, the Laston Medal from the Geological Society, the Arthur L. Day Medal of the Geological Society of America, and the Presidential Award of the Soil Science Society of America. Additionally, she holds honorary doctorates from the Paul Sabatier University in France and the University of Lausanne in Switzerland. As you can tell, Sue gets a lot of awards, and she deserves every single one of them. On a more personal note, Dr. Brantley was my first ever geochemistry professor whenever I, as an undergraduate environmental engineer, was permitted to take a course with her in the Department of Geosciences during my final semester at Penn State. Dr. Brantley's unique approach to science has been an inspiration to me since that time, which was now over 10 years ago, and I could not be any happier to be welcoming her tonight. Please join me in welcoming tonight's speaker, Dr. Brantley, who is here this evening to share her research and insights into how fracking affects our water. Welcome, Dr. Brantley.
Thank you, Ben. I have to say that was a very nice introduction. And but the nicest part was just hearing that you enjoyed the classes that you took with me. I remember those classes. Well, I'm happy to be giving this talk. I'm particularly happy to be giving it to University of Calgary. It's exciting. I'd much rather be up there. I'm a skier and I've been up that way and skied at Lake Louise, and it's just too bad that the world is in the state we're in right now with COVID and we're not visiting one another. But I'm very happy to talk about how fracking affects our water and give you some insights into work that we've been doing at Pennsylvania. This talk is really based on a lot of other people's work, and you can see some of the names here. But let me just particularly call out Tao Wen, who is now an assistant professor at Syracuse University. And you'll see his name on a lot of slides. So just to make sure we're all in the same space, and this is a public lecture, so thought I'd start with the public. I've often found that when you talk about fracking to the public includes all the different aspects of development of shale gas, of which fracking is just one of the pieces. And then to petroleum engineers, fracking is a very specific procedure used to fracture what we call unconventional reservoirs with high volume, high pressure hydraulic fracturing, which I abbreviate sometimes as HVHF. Now, fracking has actually been around for a long time, maybe back to as early as the 40s. Petroleum engineers would put different compounds into boreholes to try to fracture the rock to loosen it up so that oil or gas could come out. But it's only been recently that we started using these high volume, high pressure techniques, which is what when people talk about fracking today, they're typically talking about. And this is a drill rig here in Pennsylvania on the left, and then on the right, you can actually see a scanning electron micrograph image of the Marcellus Shale, which is the shale that most of the fracking today in Pennsylvania is targeting. And the whole point is that this is what we call a tight rock. It has very low porosity and low permeability. And the organic matter that's in here, and you can see it in gray, often has bubbles in it. And these bubbles probably formed and still contain the natural gas. And so the natural gas is stuck in here and the rock needs to be fractured to get it out. And that's why it's an unconventional reservoir. Conventional reservoirs would be more porous and more permeable and would not need these high volume, high pressure techniques. So since about 2005, these technologies have allowed the USA to reduce crude oil imports by more than 50%. And the US has now become a gas exporter. And this is really sometimes talked about as the shale revolution. And you can see assessed basins around the world with resource estimates. And I just wanted to point out, of course, this talking about fracking, it's kind of like carrying coal in Newcastle, if you'll let me put it that way, because you're sitting in one of the most prolific basins in the world. So I hope you'll be interested in what I have to talk about. I have been working mostly in Pennsylvania, but I think there's something to be learned, and the geology around the world is both heterogeneous, but then there are some similarities as well. So I like to show this. This shows the number of gas wells each year starting in 2004. Here's Pennsylvania right here, the state outline, Lake Erie here, West Virginia and Ohio. And the first well was of these types of wells that was developed with this type of fracking was drilled in 2004. And you can see that we're up to now 12,000 wells and the development was very quick. And this is part of my story is the impact of this very quick development in this area. As of 2013, more than 60% of the natural gas in the US is shale gas. And the Appalachian Basin, which is what Pennsylvania is part of, produces 45% of this. My state, Pennsylvania, is second in the US in producing natural gas. And Jeremy Weber at Pitt likes to say, if we were a country, we'd be about 6th in the world in natural gas production. But after the first shale gas well was completed in Pennsylvania in 2004, more than 4,000 complaints were logged to the state regulator over the next 12 years about problems with water. And this became really a worldwide, well-acknowledged sort of controversy is what was fracking doing to the water. And you can see some of the pictures that became famous. This is from Dimmock, Pennsylvania. There was famous actors and actresses became involved. This is a flaming water well, not in Pennsylvania. This, I believe, is out in Wyoming. And then this is a methane geyser. It's not a true geyser, of course, but a well caused natural gas to blow up water into the air like a geyser, and it was reported in my state. The most common problem was gas, natural gas, which is mostly methane, getting into drinking water, at least in Pennsylvania. And perhaps because of all this that happened in Pennsylvania, in other words, perhaps because of what happened in my state, this type of fracking was soon banned in parts of the world. And here's some of the places where it's been banned. At the same time that celebrities became involved, movies were made about it. And, one small state, Pennsylvania, really affected the world. So part of my talk is about, what we can learn about what happened, but also, why it happened the way it did. And it's kind of puzzling in some ways because Pennsylvania is the state in the US with the longest history of commercial hydrocarbon extraction. It may be even the longest history in the world. We have more than 500,000 oil and gas wells, and I think this is not dissimilar from the kinds of numbers in Alberta. And now we have these 12,000 shale gas wells, but they're on top of many, many conventional oil and gas wells. And this is a photo of the Drake well, which is purported to be the first commercial oil well in 1859 in northwestern Pennsylvania. We're also the third largest state in the production of coal. And so our state and many of the people in the state knew a lot about oil and gas and coal. So what happened that was new in 2004? What is this new technique? And there's really two parts to it that made it possible for us to start to get oil and gas out of these very tight rocks. The first part is for a long, long time, we'd been drilling vertically, but we had learned to then bend the wells and drill horizontally. And so horizontal drilling for very long distances, kilometers, they're getting longer and longer all the time, is part of what allowed this shale gas revolution. So the drilling kicks off and it follows the shale. And then to get the gas out of the shale, this is the part that has to be fracked down here in this, what's called the lateral. Now, we're of course drinking water from up here. And so what we need to do is to keep the oil and gas and any of the chemicals involved out of our drinking water. And so to do this, the borehole is cased, and a casing just means a steel tube, and it's telescoping. So the surface casing at the top is the widest, and then there can be an intermediate depth casing that's has a narrower outer diameter. And then at the bottom, you have your production well casing. And these can all be cemented with their annuli cemented so that you can keep gas inside the borehole and you can't mix it into the drinking water. So the actual fracking works like this, and I'm not a petroleum engineer, but this is my understanding. Here is your lateral borehole, and the first thing that is done is a perforating gun is put into the system so that you can perforate holes into the casing, and then millions and millions of gallons of water are pumped down with chemicals, and I'll show you the chemicals, I think, in the next slide, and sand. And they're pumped in segments of the lateral. So each segment is separated from the previous one so that you can hold a very, very high pressure. And then this high pressure, high volume of water with a lot of sand is pumped in and it cracks the rock. And this is just sort of an artist's rendition of what the fractures look like. And the sand is actually pushed out with the water and the chemicals into these fractures. And then that sand holds open the fracture. And this is all shale. This is that lateral layer of shale. And then natural gas can start to come out and get back into the well. And eventually, when the valves are opened at the top, the gas can return to the surface. So when the fracking is actually happening, there has to be a large amount of water, and then there has to be tons of sand, and sand has become an important commodity to move into these production areas. And then this is the actual fracking valves or rig. And when I've been on a site that they'll have the pumps that come in to create the high pressure are actually trucks. So they have many, many trucks in order to be able to frack often more than one well on a given well pad. So the water that's pumped down is not dilute water. It is got a lot of different chemicals in it. And this cocktail, there's more than 1,000 different chemicals that have been reported, but these are the types of compounds that are put in. Acids help the fractures form. Friction reducers make it so that it's not as costly in terms of pressure to push the water down there. Corrosion inhibitors, biocides, a lot of different gels that kind of hold the sand to push it into the fractures. And one of the things that has upset the public, of course, is that many of these compounds are toxic. Not all of them. There's a lot of materials here that are not toxic, but certainly biocides and some of the other compounds are toxic. And they are being pumped down through the depths of our drinking water down usually kilometers into the subsurface. So I like to show this to scale. This is Pennsylvania, Lake Erie again. This is the Appalachian Basin, and you can see that depending on where you drill your well in the western part of the state or up here in the northern part of the state, the Marcellus shale is going to be present at different depths. And there's a couple other things that are important here. Namely, there's often more than one shale. And so there are shales at intermediate depths that often have gas as well. And today we're even going to a deeper shale, the Utica shale, for example. The other part about this is that when these materials were laid down and deposited millions of years ago, they also trapped water. And this water is very, very salty. This, for what we call formation water, is something like 7 times seawater. And so that formation water actually comes back up when the valves are open at the surface. And so not only are we producing gas, but we're also producing a lot of water. And in fact, there's more water than there is gas in many ways. In the Appalachian Basin, I think I have my last slide back here. I mentioned something like 4 million gallons per well for fracking. And only about 10 or 20% of that frack water comes back up. And it comes back in the first couple of weeks as flowback water. And that's when those compounds can come back up. The rest of it stays down in the rock. But over the period of the well, the lifetime of the well, over years, not only does the well produce gas, so gas is coming up. This is a picture of a well pad, a functioning well pad in Pennsylvania, but all this brine comes back, this very, very salty water. And in fact, the water gets saltier with time. So it starts as flowback, it's not salty, gets saltier with time. So there has to be a separation between the gas and the brine at the well pad, and that's what you'll often see on these well pads where the brine is collected. Then the brine has to be either pumped away or trucked away, and it has to be disposed of. So how can water be affected? Well, there can be direct contamination from the depth of the reservoir. The frac fluids could somehow get into drinking water. Emission of natural gas, spills or leaks, and these spills can be from drilling fluids, fracture fluids, brines, or there can also be leaching out of shale cutting, so all the shale that was drilled in the borehole. Erosion problems, this is not something I'm going to be talking about. And then issues that are related to the fact that almost every basin that's being fracked with these new techniques already has a lot of oil and gas wells and coal mines as well. And I put this picture in here just to remind me to introduce myself. This is me kayaking with my husband. I'm a geologist. I consider myself an environmentalist, but I'm also pragmatic. And I think geologists know that we live from resources in the earth. And so I always came to this problem thinking about it from, we need this energy, but we also need water. So I want to kind of pose the question of what happens to our water in that respect. All right, so let's look at the thing that in many ways has worried most people, and that is, this is a depth, and then this is a lateral. This is a picture from an oil and gas publication. This is, the fractures around a lateral. This lateral doesn't look very flat in this picture, but they're not always completely horizontal. But here is the rock in between, and here's the drinking water. So this is sort of the canonical image. These fractures don't come anywhere near our surface water. So there's no way for these compounds that go down to get back up to the water through this rock. And I think that's true. I don't know of any cases where, the compounds went through a, very deep set of rock up into the surface water. But there are cases where the frac compounds are pumped down. And then if there's some kind of blowout, sometimes communication with older wells have allowed the compounds to come back up again. There have been some reports of cementation problems. And all of these except this one that's in red here, which I've actually worked on, all of these I have put into this slide based on a study from the US Environmental Protection Agency. I haven't worked on any of these other sites except this one, which I'll talk about later. today. So yes, compounds can go down and come back up into drinking water, but it is extraordinarily rare. There's, probably 1 million wells that have been fracked. It's very rare. This is probably the least of our worries. The most common mechanisms for shale gas waste to get into water resources are the following. A lot of the problem is with the brines because there's so much brines that are being produced. And in Pennsylvania, initially, the brines that were being produced, they could be disposed directly into the river through a publicly operated treatment work. And these are water supply um, uh, systems that don't take salt out of the water. So this was an extremely bad idea. It was like, putting salt water almost directly into the river. And there's a fair amount of bromide in these brines. And it turns out that when drinking water was being pulled out of the Allegheny and treated with chlorinated compounds, some of them became brominated, and there was some real worry about that, and the EPA made this process stop. Spills on well paths or with trucking or injection, the brines in the beginning were trucked to other states and injected to get rid of them. Nowadays, the brines are actually typically used to hydrofrack new wells when fracking is going on. Another way that the compounds can get into drinking water is from leaks from well pads or from pipes. And then also early on, I show this impoundment here. This is a water impoundment, but early on they had impoundments that would have frac fluids or sometimes impoundments with brine. And there was a lot of leaks from those that created some of the problems that you've probably read about that were very, very problematic early on. This is just to kind of convince you from 2005 to 2020, this is the number of drilled wells in, let's see, in red, the number of fracked wells in blue, this is in Pennsylvania, and then the number of spills. And you can see they all were kind of tracking one another. And of course, I just want to emphasize this was something that was possible early on. It was made illegal in 2011. And then impoundments now that are used in our state can only be water, fresh water. They can't be brines and they can't be frac fluids because those were early on observed to create all sorts of problems. Now, I just told you these are the ways that are most common for waste to get into our drinking water. There have been lots of studies where people have gone out and monitored water wells all over and tried to figure out if there's any problems or any evidence for problems from shale gas well development. And these are only 4 of the studies that I know of, including one in Alberta. And almost everyone, perhaps everyone, has concluded that they see very little, if any, influence on water quality. And I think the reason for this is that there are some problems, and I'm going to show you some problems that do happen, but the frequency of these problems is very low. And if you do a forward kind of study where you go out and pick some wells, water wells, and study them around some shale gas wells, the likelihood that you're going to pick one of the sites that's a problem is very, very small. Now, on the other hand, all of these studies tend to find that a lot of domestic water wells have contaminants in them. And a very common contaminant is methane. So there's a lot of natural methane that's produced that gets into our drinking water. And sometimes the natural methane can be at very high concentrations as well. This is in Alberta, but in Pennsylvania, I think a quarter of the domestic water wells in Pennsylvania have some detectable methane in them. And in some parts of the state, it's higher than that. So in 2011, I wanted to help on this. There was a lot of public furor in my state. I didn't understand what the problems were. So I proposed to put together a water quality database and pull together data from watershed scientists, government agencies, industry, nonprofits, university personnel, pull it all together, put it online, talk about it, and run workshops about it, and bring all these different types of people together to talk about this and to try to figure out what was going on. This just shows you how our database has grown from 2010 to 2020. We have more than 1 million data values, mostly in Pennsylvania, some in the surrounding states. And we include data from watershed groups, and they come to our workshops and discuss implications and that sort of thing. And then we publish the data. We also publish papers about it. So I did mention that the most common way that wastes get into the water is from spills. In Pennsylvania from 2007 to 2014, there was about 1,300 spills reported. 76 of them were larger than 400 gallons. Some of them were absolutely huge. They were reported in Pennsylvania. Some of them didn't leave the well pad. We looked through our database and we have designed even a very sensitive statistical network technique, not really a statistical technique, but a network technique to look across the 70,000 kilometers of river water mile in Pennsylvania and try to see if we can see the impact of these shale gas well spills in our state, in our database. And maybe heartening or disheartening, we see, I think, 3 spills. So something like 0.2 to 2%. This range is simply how tight you make your statistical control. Because what do we have to do? We have to compare the upstream chemistry to the downstream chemistry. We have to know where the spill was. And there's all sorts of variability in water chemistry over time. It's very difficult to convince yourself you're seeing any spills. I think at most we could convince ourselves we see 3. Why do we see so few in our database? Well, it could be because most of the spills were small, mostly were contained on the well pad. Maybe because the spills were quickly diluted. It rains a lot in Pennsylvania. Maybe the contaminants were biodegraded or they're obscured by, sodium chloride is one of the things we look for. Well, there's a lot of sodium chloride in our streams in Pennsylvania because of road salt. Monitoring is very sparse. I think the main reason is that monitoring is sparse. If you have 12,000 shale gas wells and 70,000 miles of streams, it's very difficult to even imagine how you would ever be able to detect spills that are diluted very quickly. So we also started working with volunteers. We worked very much with Trout Unlimited. This is one of my grad students, Josh Woda. And this was a way of collecting more samples and then also doing education and learning about the landscapes. And we did. The volunteers led us to unplugged wells. They increased our spatial coverage. They increased our knowledge. They learned with us alongside because they would come to our workshops with industry, the U.S. Geological Survey, and the Department of Environmental Protection, the state regulator. Volunteers led us to abandoned, orphaned, and aging oil and gas wells. The unconventional wells are in red here. The gray are the conventional wells, and there's something like 500,000 of these in our state, and they're not even all mapped. So no one knows where these all are. This is Tawen, who I mentioned earlier. You can see that some of these wells are degassing very visibly. Volunteers in the U.S. Geological Survey also led us to identify a new type of discharge that looks like acid mine drainage. If you've seen drainage coming out of coal mines, it tends to look like this. This is not acid mine drainage. This is gas leak discharge. And this is methane that's coming to the surface. And it turns out that it changes the water chemistry and it mobilizes metals so that when they come to the surface and precipitate, you see this basically iron oxides or rust. This is in the Allegheny National Forest. This is from an old conventional well. This is from what we think is leakage from a shale gas well in central Pennsylvania. And when we studied that site, the stream is called Sugar Run in Lycoming County. When we studied that site and collected data from the area and looked at data that was available online because it had been studied by the state regulator as well, what we noticed was that if you plot concentration versus time, in the beginning, in this stream and in these areas, the methane was low in concentration, and then the methane went up. This is a schematic, of course, but we do have some data published in the literature that shows some of this. As the methane concentration went up, turns out methane can react with oxygen, especially in the presence of bacteria that can catalyze the reaction. So it pulls down the oxygen, and then when the oxygen is gone, it actually can react with iron 3 and reduce it to iron 2. Iron 2 is more soluble. So as the methane goes up very soon thereafter, you see the iron 2 go up, and it can also solubilize manganese by reducing it as well. So your metals go up, and you have typically a little bit of sulfate even in these fresh waters. Eventually, when you start running out of some of the metals, then the methane will be used by bacteria to reduce the sulfate to sulfide. Once the sulfate goes down and you start making some sulfide, sulfide will react with your iron and manganese in the subsurface and pull it back down. So we saw this kind of evolution of iron going up and methane going up, sulfate going down, and then H2S going up. And we realized that this was kind of a signature for what it looks like when new methane comes into a system. And this is our picture of what the subsurface kind of looks like. We think there is a leaking shale gas well. We think the plume of gas moved out over time. Here's the stream up here. Here's the seep over here. And in the front of the plume, methane is reacting with oxygen, and then eventually there's no oxygen, so then it's metal reducing and then sulfate reducing, and the plume got bigger over time. And you can actually see this in the data. And now the plume has actually moved sort of beyond this stream, and it's in the next stream over, we think. So with this work, we now have more than 20,000 stream and groundwater data for Pennsylvania. Most are probably naturally contaminated by methane. Only a few are putatively contaminated by development of oil and gas wells and shale gas wells, like we think in this particular case here. Here's Pennsylvania. Each of these circles is a water sample, and the size of the circle tells you how much methane there is, up to greater than 28 milligrams per liter. And you can see who collected these data. So you can see that we do have volunteer groups, but we also have academic institutions and then Pennsylvania Department of Environmental Protection, and then also gas companies. Most of our data actually comes from the gas companies. They give the water sample data to commercial analytical laboratories, and they give it to the DEP, and they give it to us, and then we collate it and publish it for the public. So we know a lot of this is natural methane, but we also know that there's some cases where new methane has leaked into water systems. And there are studies of this that the Department of Environmental Protection have done. And there's expensive isotope measurements that can be done. There is nothing that's a fingerprint that you can say, yes, indeed, it comes from this well. Typically, you have to do a very long, detailed analysis, geological and isotopic and geochemical. We started realizing that we have 20,000 water samples. They each have like 40 analytes in them. That's a big data set. We thought we could use some new machine learning tools to try to look for signatures. Is there a signature, and I'm kind of hearkening back to this, a signature that might tell us that the methane is new. It's not natural methane that's been a long time. It's new methane that's moved into a system. And so we started looking for it with these data sets, and we played around with lots of different techniques. And this is just a graph to kind of show you what the computer does much faster. This shows you calcium over manganese or plotted versus barium over manganese for a whole bunch of groundwater samples. And then we color coded them. This was work by Josh Woda and Tao Wen. Color coded them to show that they either have low methane or they have high methane. So the red colors tell you the high methane. And many of these high methane samples, we have no reason to believe are contaminated. These are natural high methane samples. And then these, we also think most of these are natural but low methane samples. And then when we look at our sugar run samples, the ones that we've worked very, very hard on, we think putatively anyways, contaminated by shale gas wells. When you plot those down there and those little stars down here, you see that they're high methane, but they're plotting where they should be, according to the big data set, they should be low methane. And so what I'm trying to show you is that this pair actually there's 4 analytes here, but this pair of ratios can actually highlight that this is new methane that's come into this system. And when the computer does this, it doesn't have to look at just 4 analytes, it can look at all 40 analytes and all different pairings. And then we try to figure out, using what's called machine learning, to see, can we train the computer to figure out what's new methane, which we often call anomalous methane, versus what is natural methane. So we've done this now, and this is work by Tao Wen that's soon to be submitted in the Marcellus. We've done it in the Denver Basin and Raton Basins in Colorado. And then we've done it in the Haynesville, Barnett, and Eagle Ford down in Texas. And we use as many data as we can. So in the from our data, we train it to as many data points as we can, and then we hold out some data to test it on. So these are our holdout data trained on all the rest of the data. And what we saw in this holdout data, 64 had high methane, and of those 64, 42 using this kind of machine learning of those look like they are anomalous methane. And the way we quantify this is we look at all different pairings of all different analytes and predict based on all the different pairings with some kind of, how many of these different models predict that it's anomalous methane. And there was 42 out of 64 were predicted to be anomalous methane in the Marcellus. We have a smaller data set in Colorado. So for 457 water samples, 58 had the high methane. 4 of them are predicted to be anomalous methane. And down in Texas, where we have the smallest data set, 338 water samples, 34 with high methane, 0 were predicted to be anomalous methane. So the upshot of this is that the histograms are showing that the machine learning suggests the incidence of anomalous methane, fugitive methane in the Marcellus, so in Pennsylvania, is higher than in these other two locations. So why might that be? Why might there be more problems in the Marcellus? And can we predict where these problems are ahead of time? That would be something that would be brilliant to do. And so we're going to go back to our data set now again in Pennsylvania, and we're going to go up here in Bradford County. This is one of the centers of drilling. The two centers are here and here. And here now is Bradford County. Here's all the data that we have in Bradford County. It's colored now for methane. You can see up to greater than 28 milligrams per liter. And it's up here in the northern part of the state. And now what we're going to do is Jesse Lee and grad students that we've worked with in the computer science department design this technique where you take a window, and this is, in this case, it's a 5 kilometer by 5 kilometer window. And with the computer, you move it across your region. And then in that box, in that 5 kilometers, you look at every water sample in there. And then you look at the shale gas wells that are in there. And I don't have those plotted right here, but you'll see it on the next graph. And in that box, you calculate, in essence, the correlation between methane concentration in water samples and proximity to shale gas wells. And you calculate whether it is statistically significant, if you see a statistically significant correlation. And then we plot it, and I'm really, giving this whole technique short shrift. We plot it on a graph as a heat map. So the long and the short of it is, if there's increasing evidence of correlation between methane concentration and proximity to shale gas wells, you'll get a darker color. And this is the methane increases towards the well is red, it decreases away from the well in blue. And so here's Bradford now. Now you can see the shale gas wells on here. And you can see that there are places, and then we've kind of gone in and looked at shale gas well information. And these wells that are starred here are kind of an indication, a guess of which of these shale gas wells may be causing this heat map to show methane increasing closer to shale gas wells. Now, why is it different in Pennsylvania? I think one of the reasons is because there's more folding and faulting in this northern part of the Appalachian Basin than those other basins that I was talking about. Now, I don't know this is a hypothesis, but here's, anticlines and synclines. This is just showing you along the axis is a red line, and along the axis of a syncline is a blue line. And you can see this is an anticline axis, this is a syncline axis. So I think that it's related to this. And we can run our sliding window in the same way, but instead of calculating the correlation with instead of asking the question, does methane increase closer to a shale gas well, we can ask the question, does methane increase closer or further away from a anticline or syncline? And I guess I should have pointed this out. This is very small. This is only 7 out of 1,400, like 0.5% of the wells that we think could be showing some kind of leaking problem. Now here's the calculation of the sliding window showing a correlation with proximity to the nearest anticline. And what you see is the water closer to this particular anticline, which I think is the Tawanda anticline, tends to increase in concentration in methane. And so this is probably natural. This probably doesn't have anything to do with the the shale gas development. And the wells that we think up here are problematic, that possibly are leaking, they plot down here, and it doesn't look like that there's anything about the anticlines that you can really explain this coloration here. But down here it becomes much more difficult to say whether this methane concentration in water down here is natural because it's related to the anticline, or if maybe it is somehow exacerbated by shale gas wells. And this just shows you what we think, one way to think about this. Here's an anticline. These are all faulted in Pennsylvania. So this is a fault, and we think that gas can move up along the faults, and then gas can also pool in the top of an anticline, and then maybe it kind of seeps out into the fault and gets to the surface. You can sort of see a picture of this idea up here. So this is all based on mapping and statistics. Is this really happening? Well, I think it is. And the problem with everything I've done so far, it's really kind of trying to give you a sense of the frequency of problems. So I'm kind of looking statistically and regionally. But, with what I just showed you, I can't prove to you that this gas well is leaking or this gas well is leaking. The only way you can do that is going in for a case study. And so we have worked on a couple case studies that are very time intensive, data intensive. And this is one of them. This was published, first author is Garth Llewellyn, published, I think it was in, when was this, 2015, maybe. And this is actually this location right down here. And if you look up here, our statistical technique did not find it, but it does show some evidence in the map with the anticlines. But anyway, here is a fault that is expressed at the surface. Here's 5 shale gas wells that were drilled. Here are some homeowners that live right over here, and this is a picture of their lawn. And what they noticed was they had very nice water in their domestic water wells, and then they began to see methane. This is dissolved methane versus time. Shortly after the wells were drilled and after one of them was fracked, they started seeing very high methane concentrations. And so there's been a long series of studies by the DEP, and then we also studied. And what we think happened was that these wells are projected to the front of this block here. And you can see these wells were drilled through shales at intermediate depths that have methane. These sort of greenish things are what they call gas plays. So that's where gas shows. And so what I think was happening was gas was getting into these boreholes. It may not have been in every well, moving up. And then here's where this is just projected to the forward. So it's actually back here. The gas can move along this fracture in the plane of the fracture, and then can move up along bedding and get down into these wells. Interestingly enough, gas also was bubbling in the Susquehanna. You can just see the Susquehanna River here. So here's one of those synclines, and here's that fracture trace. And I really think that the interplay between these is part of what was going on. And then I just wanted to mention, they also got 2-BE, 2-butoxyethanol, came into their water wells down here. And this was also attributed to these shale gas wells. And if you want to ask me a question at the end, I can tell you what I think. You know, there's several ideas for where this it's called 2BE, typically people call it 2BE, came from, but it was definitely related to some of the activity up here. At least I think it was. That's the best explanation. Now, another case study that we did is back here at this first example I showed you in Sugar Run. This is also a big fold. There's wells right here, and the problems were up in here. And we did some calculations and calculated the curvature at the depth of the Marcellus. And the red colors show you the very high curvature. And rock that is bent with high curvature is going to fracture because rock is brittle. And so we think that probably the best explanation here is that this was this was the shallowest drilled Marcellus well in Pennsylvania. We think there was fractures up in here because of this high curvature. And we think that there was some leaking because of this intermediate depth gas. I should mention, when these wells were drilled, it was legal to not put in intermediate depth casing and cement it in. Now in Pennsylvania, the intermediate depth casing has to be put in because of this problem, but we had to learn about it before it became legislated. So what are my conclusions? What am I trying to let you go home with? First of all, it's extremely rare that fracking itself affects water supplies, but accidents have happened. And I think the biggest problems are when there's very shallow depths to the target. I think the overall process of development of unconventional reservoirs does affect our water, but the incidence is really pretty low, at least as best I can see from the data. Only a very small fraction of shale gas wells, and there maybe are hundreds of spills, but it doesn't impact a huge area, and these spills are transient features. To quantify this, really, it's very hard because there's so few problems, at least in the data that I've seen. And then to understand when there is a problem, you have to do very intensive case studies. I think that some areas are prone to more problems than others, and I tried to show you that with the methane. Looks like northeastern PA is worse than southwestern PA, and maybe the southwestern PA is similar to Colorado and greater than Texas, and certainly than Arkansas, which I didn't even talk about. I've got a student, Sam Shaheen, working on this now. But our big problem is that data are sparse, and we really need more data sharing. Now I need to stop, but let me just remind you, it's not all bad. When we look at the groundwater data in Pennsylvania from long ago and compare it to the data today, in this part of the state where the shale gas drilling is so intense, we actually see a slight statistical improvement of groundwater quality, but we don't have a lot of data from historical times. So statistically, the strength of our argument is not very strong, but if we see any effect of the shale gas drilling up here, it's that it's getting better. And I don't believe that the shale gas is the development is making it get better. I think we're getting less acid rain in Pennsylvania, and we're getting less acid rain because we're cleaning up our coal burning power plants and we're switching from coal burning to natural gas. Jeremy Weber at Pitt has looked at how much money people are getting in Pennsylvania, and you have to remember that we have to drink our water, but Jeremy estimates that almost $3 billion in royalties and associated income have come into Pennsylvania residents. And you can compare that, he compares it to how much Pennsylvanians in 2017 got from unemployment, 1.9 billion. So there is an economic effect that helps standard of living. And then switching from coal to natural gas releases less CO2 per heating unit. And the US contribution to this increase in CO2 versus time, this is the data from CO2 in the atmosphere versus time. Everyone knows this is causing climate warming. Our contribution has gone down because we are burning more methane and less coal, and this produces less CO2 per heating unit. Now, the sticker is that methane is also a greenhouse gas, and it's also leaking, as I've showed you. And it turns out it's a worse greenhouse gas than CO2, but it disappears in the atmosphere after a certain amount of time. So it's a little complicated to figure out, how much methane would you have to leak to make up for the fact that burning natural gas releases less CO2 than coal per heating unit. It's about 3% of the production. And so far, there's a lot of argument about this, but so far it does look like the gas leak rate is lower than that 3%, which means there is a net improvement in terms of climate for switching from coal to natural gas. But again, this is still being argued through. So I gave you these conclusions, but I want you also to remember shale gas development has also moved the world economy away from coal. And I think that is improving our climate, and I think it's improving our water. But then I also want you to remember that digging up hydrocarbons and burning them is changing our climate no matter what. And leaving boreholes that leak gas into the future is a really bad idea. So we've really got to figure out how we can move away from hydrocarbons. But the impact on water is perhaps not as bad as some people have suggested it is. I could also give you a whole bunch of non-technical conclusions, and I'm just going to stop here. But I do think that this problem is not just a technical problem, and helping the public make decisions and stakeholders make decisions is not just a technical problem. So thank you for this opportunity.
And thank you, Sue, for sharing your research with us this evening. I really enjoyed hearing this history of Pennsylvania. I left there in 2010, so I didn't know much of this more recent advancement. So I'm very happy to have learned that tonight. My first question for you, before we move on to questions and answers from anyone in the audience, and you can type them into the Q&A box at the bottom of your screen. Of course, we appreciate all of your questions, but please be advised that due to limited time, we may not be able to answer all of them. My first question is about, you did say that some industry partners have been providing data. I mean, so I guess that's not mandated in Pennsylvania. Is there an effort to perhaps make that more necessary or more frequent?
Yeah, I didn't really completely explain that because of timing, but in Pennsylvania, when a company goes out and wants to drill a new well, they don't have to take water samples, but nowadays they always take water samples within the setback distance around them, which is like 2.5 kilometers. And they get a certified consultant to take the waters, and then they take them to a certified analytical laboratory, and then they give the data to the state regulator. And if they do that, then if one of those people complains that their water has been impacted, then that data can be used to help them defend against that claim. So that's why the companies do this, and that's where most of those 20,000 groundwater samples came from. And it's been going to the state regulator on paper and then as PDF. And only recently have they started to get it electronically. And so we made an arrangement with the regulator for them to give us the data, and we literally type it in so that we can put it online and start to use it. And then once you get big data sets like that, I think that you can really learn a lot about your system. And I don't think I said this in one of my conclusions. I was supposed to emphasize that I think putting these data together not only helps the public understand what's going on, but if it's true that the rate of problems is relatively small, that could actually help industry too. So I think there's a lot of good reasons to share these data. And I think, groundwater, we need to know more about it. We need to drink this water, so we need to share that data.
Thank you very much for that. So I have two questions from Maureen McLeod. One, how much do you use anecdotal information about river and well water from the general public in this type of research? And two, at which point does any of the contaminated water become a problem for the environment and for the human population?
So anecdotal information, it helps us figure out where to go and what's going on. It's not going to hold up in a court of law, but it helps you know where to look and to find problems. So I think that we talk to people and we learn from them, and then we also try to teach them what we know. So that's the first part of the question. The second part was human health. and how many or how much problem is there in terms of human health. And I think I do have a slide about human health issues. That is a open question, really. There's lots and lots of studies of human health impacts that are starting to come out now. And I'm not a human health researcher. All of the studies are correlative. So they look at some measurement of human health and then try to correlate it with closeness or proximity or distance. I'm not seeing my slide. It's in here somewhere, I thought. But there's lots of different things that people have studied. They've looked at asthma. They've looked at birth weight. They've looked at headaches. They've looked at breathing problems. I don't know where that slide is. Oh, there it is. And this is just a couple of them. This is just two that I put together. But again, they're always looking at incidents of some observation about humans versus like proximity to shale gas wells. I don't think there's been a single study that has showed, an exposure pathway that shows, contaminant from shale gas going into someone's drinking water, and then a study that could show that there was a human health effect. But there's more and more of these studies coming out where there does look like there's statistical evidence for correlation, and that makes you wonder what's going on. If the incidence of water problems is relatively low, then if these health effects are real, then it's possible that it's not the water that are causing these health effects. And if it's not the water, but they are real, it's probably air emissions. And I think there are studies about air emissions close to some of these wells and close to compressors and that sort of thing that may be more related to the health, maybe than the water. But we still need to study it.
Yeah, thanks for that. So the next is an anonymous attendee who asks, to what extent do you expect known and additional mechanisms may affect water quality on a longer time frame, for example, 50 to 100 years from now?
Well, that's a good question. One of the studies in Pennsylvania that was published in 2012, I think they looked at 200, this was by Beth Boyer, she's at Penn State also, looked at 230 wells throughout the state where within, I forget what it is, like within a kilometer of a shale gas well. And, they looked at it over a period of a year and they saw no change in that water chemistry. So I think what the question is if you studied those same 230 wells over a longer period, would you see change? And I believe that the Penn Staters are going out to do that over a longer time period. And the jury's out, we don't know. Now, having said that, if you look at the old oil and gas wells, they tend to start to leak. Now, they were not cemented and plugged and sealed with the modern methods that we have today. We're much better at it today. We can seal them up much better, but we cement them up with cement, and cement does dissolve, and earthquakes sometimes happen, different things happen. You can get cracking in the cement. My guess is these boreholes, even beautifully plugged and sealed boreholes, are, over the 50, 100, and then beyond time frame, I'm not sure that they will hold for that kind of long time frame. And that's why one of my last points of one of my conclusion slide was, we're putting all these boreholes out there that are going to be letting methane get to the atmosphere or into our aquifers, and that's not a good thing.
All right, thank you. So the next one is from your former colleague, I believe, and upcoming Gallagher lecturer, Paul Moban. Have there been radionuclides in groundwater or surface water associated with fracking?
So the brines in the Appalachian Basin have the highest concentration of radionuclides, I think, than any shale gas basin in the country. And so there has been a fair amount of study of this, particularly with radium, looking at radium. And I don't think that anyone has seen significant radium in any drinking water, any water resources that you can attribute to shale gas development. Now, there are parts of Pennsylvania where for a long time it was legal to take brines from conventional oil and gas and essentially treat it a little bit, but essentially let it go into streams. And over a long period of time. So those brines are not any different really than shale gas brines, but it was legal for a long time in conventional oil and gas. And there have been some studies in those streams, some really interesting work by Nat Warner out of Penn State, where they've looked at, they use mollusks that take up different elements. And I think they've seen some evidence that, some of those mollusks have taken up radium, if I'm not mistaken. But again, I don't think there's any radionuclides that have gone into people's drinking water that I'm aware of. There have been some studies of radon, and I don't know as much about that, but there is there's more work to be done on the radon question, which is a radioactive gas with a very short half-life.
Thank you. So the next question is from Scott Jess, who is a postdoc in our department. He says, thank you for a great talk. Are your results showing a particular way in which gas is entering water systems? In other words, breaks in casing, movement along faults, poorly plugged wells, etc.
So I worked on a paper with Pat Hammond, and it looks like most of the gas leakage is when wells are not cased and cemented across their entire borehole length adequately. So I think when they're adequately sealed, cemented, cased, then the gas isn't getting out. But so that's how it's getting out of that borehole or moving along the borehole if it's coming in from an intermediate depth shale. Now, when it moves up into the aquifer, then it can move either as a dissolved species, so that you can dissolve methane in water, or it actually moves also as free gas. So you can actually have second phase gas. And both can move, and it's very complex knowing how to model that. I mean, that's what petroleum engineers know how to do, right? Is two-phase flow and that sort of thing. And there's some great work that's been done up here in Canada by, I'm not going to remember the right names, but where they've been actually pumping down methane into some aquifers and actually studying how it moves and how it partitions. I think it's Cahill and Roger Becky, if I'm not mistaken, where they're actually pumping the methane in on purpose and then following how it moves through the subsurface. It's very complicated because it can be degraded by bacteria. The methane can be actually used as an electron source. The methane changes with seasonality. There's a lot of work to be done about methane in aquifers in the subsurface. And then when it gets into the stream, it can actually move in the stream for quite a while before it degasses. It eventually will degas out of the stream. And there's work to be done on that as well.
Excellent. Thank you. So Rajiv Nair, geochemistry professor in our department, says that you mentioned that in one of the problem areas, the methane was coming from shallower gas plays. Are there specific geochemical signatures that you can use to fingerprint gas from different formations? What evidence do you have for the conclusion that this shallower gas play was the culprit?
Yeah. Well, okay, so I think he was asking me about this study back here, which is Sugar Run in Bradford County. It's funny how both the case studies are Sugar Run. Interesting to me. Anyway, I think he's looking at this study. So yes, there was a lot of work. This site was litigated. The first author, Garth Llewellyn, was the consultant for the homeowners. Let me shout out for the homeowners. They litigated, but when they settled with the companies, they insisted that all the data become public. This is one of the biggest problems, is the data, when there is a problem, the data typically doesn't become public. The companies don't want it to go public. And so, after litigation and a lot of pain and suffering around that, the data don't go public. But this site, all the data are public from litigation. So we published all of that. You can go to this paper and look at it. Typically what's done is carbon isotopes, hydrogen isotopes, oxygen isotopes. We show a lot of the isotopes in the paper. You look at the methane to ethane to propane ratios. There's some of that data in the paper as well. There's nothing that's a perfect fingerprint, though. There's, you know, these isotopes that people often think they're fingerprints, but it's not a complete fingerprint. So the more data that you can measure, the more you can constrain the system. But you can read it in this paper better than I can tell you the whole story.
Excellent, thank you. So Dr. David Eaton, geophysicist in our department, asks, beyond water quality, what are the concerns about the volume of water used for shale gas development, especially in more arid regions such as West Texas?
Yeah. So I'm probably not the best person to answer about that. The papers that I read, first of all, in Pennsylvania, you know, there's been a little bit of problem every once in a while, like in the dead of summer or something with a little stream or whatever, back when there was a lot of fracking going on. But we have so much water in Pennsylvania. The amount of water that is being used for fracking compared to how much water is going through the system, it's really a small amount. But from the papers that I've read, mostly in the arid regions, I haven't seen a lot of people talking about it because it's regulated. But again, I am not the expert on that. So.
A second follow-up question from Paul Bowman. Given the long history of oil production in Pennsylvania, why was the regulatory regime playing catch-up to meet detrimental effects from fracking?
Oh, thank you for asking that, because I didn't quite make this point and hammer it home. And that is, I think part of the problem was the speed at which the whole rollout came. That's why I love showing that slide where you can see, all the gas wells, being drilled. It just happened, between like 2009, 10, 11. There was just like everywhere you went in Pennsylvania, there was, fracking trucks and sand and, everything was going everywhere. The rollout was really fast. And I think that was a political reason. I mean, they really wanted to get it going in the state, and the governor was very proactive towards that. And I think if we'd gone a little slower, some of these things like, figuring out that we needed to case and cement right through the intermediate depths and that kind of thing. Maybe we would have done that a little bit sooner. Maybe we wouldn't have used impoundments for frack water and then had some of that frack fluid seep down into aquifers that got into people's wells. So maybe we slow it down a little bit. We would have not had quite so many problems happen right there in the beginning. And I think part of what's interesting about that to me as Pennsylvania is, I think that kind of changed the world. All those problems that we had right there in the beginning kind of changed the world because it made a lot of people be against fracking. And we've been fracking for a long time. We just haven't been doing it with this kind of volume and this kind of high pressure and, some of these compounds and that sort of thing.
Okay, I'm going to ask two more questions and then we'll call it an evening. So first, we have a couple of questions about earthquakes. So do you think, I can summarize these, but potentially there is some correlation between fracking and earthquakes in the shallow subsurface. Do you think it's possible that these earthquakes could cause new preferential flow paths into groundwater, drinking water sources, and then account for some new groundwater enhanced concentrations of natural gas, for example?
So there's two kinds of earthquakes associated with shale gas industry that I know about. One is there are occasionally earthquakes that happen right after a well is fracked. And this has happened in Europe. It's happened in Pennsylvania, way over in the western part. I think it's just once that it's happened. Looking to see if my husband's here because he studies some of these earthquakes. The second kind of earthquakes that are happening is with all this volume of brine, most of this volume across the country is being injected into what are called disposal wells or injection wells. And if you inject enough volume at a high enough rate, you can cause earthquakes in certain places. And this has happened a lot in Oklahoma. It's happened in Ohio, probably because of brines from Pennsylvania, because we were trucking a lot of it to Ohio. So those are two kinds of earthquakes that can happen. So now the question is, can this open up new water flow pathways? I think the answer is probably yes. Now, if the earthquake is really deep, then, that flow pathway is not connecting all the way to the surface. So, I don't know anything about an earthquake that has created a new flow pathway that connected all the way to the surface, but it certainly is creating fractures. So water is moving down there, that's related to these earthquakes.
Excellent, thank you. And we have time for one last question from an anonymous attendee. And the question is, your presentation, oh no, sorry, this is from Perry Kotkus is his name. Your presentation indicates minimal detrimental effects from fracking, and how well publicized is this information? And as opposed to, I guess, the large media focus on anecdotal problems that are perhaps more negative.
Well, I mean, let's parse that question really. For the people that lived right here that had to leave their houses because of this problem, the gas company never fixed the problem, or maybe they fixed it, but they bought the people out. This was a huge problem. So, talking about anecdotal problems or case studies as if they're like one-off things that don't really matter. I mean, I hear that sometimes, people say, oh, that's just this one I've been told, that's just a weird location geologically. That's the only reason that happened. Well, these things do happen. So this is like a value judgment, right? Like, how many of these things do we want to have happen and then let shale gas development go on? It's a value judgment. That's not for me to decide. That's for the public to decide. And what I want to do is try to get information out and figure out what did happen in the small number of case studies that I can look at, and also try to get a handle at the frequency of problems, which I think is really difficult to do because data don't get out very easily, So I'm not sure if I'm answering his question, but I do think that because of all the problems that happened in the early 2000s, mid 2000s, and all the public pushback, that got imprinted on the public. And so we as scientists, that think everybody should look at the percents and just calculate it and then figure out from the percent what they feel about the problem, we should recognize that, once you lose social license, like we kind of did on this fracking problem, once you lose that, it's very hard to gain it back. And so maybe going slow is a good idea. So anyway, I'm not sure I'm answering his question, but I don't think most people understand very much about fracking, even people that are really against it, even geologists I know that are against it. I think a lot of times they don't really understand very much about it. It's pretty complicated.
Thank you very much. And thank you everyone for your questions. It's been a pleasure being here with you tonight for tonight's event and being able to participate in this Gallagher presentation. So I'm going to turn it over to Dr. Stephen Hubbard.
Thank you, Dr. Brantley, for joining us this evening. It was an incredible presentation, so much information, so much to think about. Hello, everyone. I am Steve Hubbard. I'm the interim department head in the Department of Geoscience. As a key objective of this colloquium, as said earlier, is to connect science with our community and our community with science. And I'm confident that today's presentation, hit that mark exactly. Really nice. I would like to take again this moment to thank the Gallagher family for their ongoing support of this public series. Our students, faculty, and staff and alumni have all been made richer by being able to learn from world-class researchers like Dr. Brantley. If you are interested in supporting our research or any other faculty initiatives, please visit our faculty website at science.ucalgary.ca. Additionally, there will be a link included in the post-event survey that you can follow. It's my pleasure to remind you that we have 2 more Gallagher Colloquium planned for winter 2021. On Thursday, February 11th, Dr. Evan Smith, research scientist with the Gemological Institute of America, will present his lecture entitled "The Finest Diamonds Hold Earth's Deepest Secrets." And then on March 4th, we'll welcome Mr. Paul Baumann, who's been active in our discussion here tonight on the chat. He's the technical director for the Advisian, who will be talking about searching for water in humanitarian crises. Should be another really fascinating presentation then. So look for registration details in your inbox or by checking our website again at science.ucalgary.ca. We are looking forward to you joining us online for those presentations. And lastly, when you see our event survey in your inbox, please do take a moment to fill it out. The link to give will be included in the survey in case you're interested in doing so. Your feedback is important and we do want to hear from you. Again, thank you for coming and enjoy the rest of your evening.